Okay, so I'm welcome to our Live and Learn faculty presentations hosted by the University of Oregon SAIL program. I'm Laura Fernandez. I'm the Executive Director for the Summer Academy to Inspire Learning program here at the University of Oregon. We are a pre-college program serving middle and high school students in their pursuit to higher education. We are so honored and excited today to be featuring one of our faculty members, Scott Fisher. Scott is an astronomer lecturer and outreach coordinator for the University Department of Physics and also the director of undergraduate studies. Scott's an expert in space, NASA, and all things astronomy. So his particular strength as well is making science and STEM accessible to non-scientists. So my hope is by the end of today, you'll be a new budding scientist if you weren't already.
Yes.
We have had Scott participate in our SAIL programs for many years now, and you will learn a lot and I hope enjoy. Scott is going to be talking about cosmic perspectives today. And so you'll be learning a lot more about what it would be like to be an astronomer and what you might study if you were to attend the University of Oregon or take an astronomy class in college. So throughout the presentation today, if you have questions at any time, please put them in the chat feature. And Scott loves to answer questions. So we are looking forward to having you with us, Scott. Thank you so much.
Thank you, Laura.
Take it away.
Oh, thank you. Hi, everybody. Like Laura said, I'm Scott Fisher. I'm a faculty member in the Department of Physics here at UO. And I got all those fancy titles that she talked about. But one more she didn't mention, which is kind of neat, is turns out that I'm the director of our observatory. We have an observatory here in Oregon, and hopefully get a chance to talk to you a little bit about that here today. So I'd like to share my screen with you so you can see some slides that I put together for the talk. So hold on a second. I'll roll up my sleeves here, and let's see if we can get some technology going. There we go. Laura, can you see that first slide there?
Beautiful.
Oh, excellent. Well, there's a picture of the sun. Let's go back to the first one instead. How about that one?
Welcome.
Yay, welcome everybody. So look, I just wanted to put a little funny title on here and welcome to the talk, and here's your cosmic perspective. And over the next half hour or so, what I'd like to do is tell you a little bit about being an astronomer and what it's like to work at big telescopes and be a scientist as a career. And then talk a little bit about Pine Mountain and a little bit of stuff that we can do here at Oregon, especially like Laura said, if you end up coming to UO and being a duck, and how you can get involved with my research group and some of the stuff that we do here. I love to start off all of my presentations with a pretty picture. And then this is one of my favorite pictures. I think you can probably tell, this is a picture of a beautiful dark sky. And that big arc that you see in the sky, that's the Milky Way. That's our Milky Way galaxy. And there's two really big telescopes in this picture. And the one on the right side of the image is actually very special to me. Turns out that I worked there before I came to UO, and we're going to talk about that for a few minutes too. So just a little pretty picture to get you started off. Let me give you a roadmap for this talk. What we're going to do is talk about a few of my favorite topics. The first one, cosmic perspective check. Can't help that. That's one of my favorite topics of all times, especially when I'm talking to students like y'all. Astronomy at Pine Mountain. We're going to talk about Pine Mountain a little bit, see if I can hook you into astronomy and think maybe come and visit us sometime once we get it back opened up after COVID. Then we're going to talk about my second favorite topic, me. You think I'm joking? No, we're only going to talk a little bit about me, but I promise that's in there a tiny bit. And then I want some Q&A. Laura is right. I love questions, and you all don't realize it, but I had 2 cups of coffee today, so I'm ready to go, peeps. And with that, seatbelts on and tray tables up. Let's start this talk. Look, my first point to you is that I think science is cool. I think we all know science is cool, but I think sometimes we kind of get it scared out of us. And I'm not exactly sure why that happens. Maybe you had a teacher that was a little mean, or you had a topic that you didn't like, or something like that. But I'm here to say that I think we are all astronomers. Me, you, Laura, Josie, the dudes that are helping us in the YouTube chat, all of us, everybody who's watching. I think we're all astronomers because astronomy is present in our lives, and things like well, gosh, how old are you? Well, we measure our age by how many times the earth goes around the sun, and we measure time by how fast the earth rotates on its axis. And by the way, I look outside, the sun's up in the sky right now, and we're active, we're all awake, and the sun goes down, and we go to sleep day and night. And we watch the phases of the moon, and I bet you $1 that all of us have had a moment where we've looked up into a nice dark sky and just had that moment of wonder, kind of that moment of awe. And that's something that I think is universal between us, and something that I like to develop as much as I can. And here's a photograph of 3 ducks. These are 3 UO students who came and visited Pine Mountain a couple summers ago. And the young lady in the middle there with her hands down, she's actually holding a remote control in her hand, and she was controlling the camera that took this picture. And they took this picture not too far from Pine Mountain out there, just to give you an example of what the sky looks like, and what you'd get to see if you got to come out and visit us next summer sometime. So let's talk a little bit about me. And like I said, it's sort of a joke, but I want you to know that I had a real interesting first career before I came here to UO. And here's a photograph of one of my favorite mountains in the entire world. This is a mountain called Mauna Kea. It's a very large mountain out in Hawaii. It's on the big island of Hawaii. And this mountain is about 14,000 feet tall, 13,796 feet, got it memorized. And just to give you a little perspective check, Mount Hood is about 11,250 feet. So if you think back that maybe sometime you saw Mount Hood, if you drove up to Portland, or you live in Portland, or you flew into Portland and you happened to see that beautiful mountain, think of Mount Hood and then take another third of Mount Hood and stuff it on top of it. And that's kind of about how big Mauna Kea is. This is a very large mountain out in Hawaii. By the way, that is snow up on top of the mountain too, if you look up there at the very peak. But look up at the very tippy top of the mountain. If I can move my mouse here and see if you can see those 3 little spots up on top of the mountain. Those are telescopes. And from where I was standing to where those telescopes are, it's about 28.5 miles. And you think, gosh, that's from Eugene to Corvallis. That's actually a pretty significant distance. And you can look up with your eyes and see those domes up on top of the mountain. And I think that gives you the first hint about how big those machines are and how big the telescopes are inside the domes. Our buddy Richard Wainscoat, down in the corner, Richard took this picture for us. Richard did a neat thing. He hired a helicopter, and he's a beautiful, wonderful photographer, and he went up and flew a helicopter around the summit of the mountain and did this picture to show there's an entire cluster of telescopes up on top of Mauna Kea. And look, so if we were little kids, I'd make you count them off with me, and we'd count 1, 2, 3. Well, there's 13 telescopes up there altogether. And the 3 that we could see from that previous picture are this one right here, this one with the silver dome, this little fella right there to the right. And this one at the silver dome is the one that's very special to me, because that is where I worked as an astronomer before I came to UO a whole bunch of years ago now. Laura and I were talking about, but that's an observatory called the Gemini telescope. And we'll talk about Gemini a little bit. But the first thing I want to do is, let me see if I can tease you and show you how big that telescope is. There's a picture that I took so many years ago now, but a beautiful blue sky. Oh my gosh, look at that clear sky. Anytime you see a sky like that, you know that you're going to get good observing tonight. And this was right at sunset when we were getting the telescope opened up and getting ready to use it for the evening. And one thing you might notice is that that's a kind of a weird looking dome. It's got those very large gates, and by the way, those gates open and close like this, and in this photograph the gates are wide open. And you might say, well, Dr. Fisher, why the heck do you have your telescope so open like that? Then I would say, student, there's an excellent reason. It turns out that what are things that astronomers hate? I'm going to list them off for you right now. Daytime. Okay. Clouds. You know we hate clouds. Why would you want clouds in the sky? Turns out we also don't like the moon very much because the moon is so bright, it wipes out the sky and you can't see the rest of the sky. Oh, excuse my eyeball itches. But then the last thing we really hate is turbulence, distortion. Look, if you're taking a selfie with your cell phone, do you want to have a nice in focus selfie or do you want to have an all jittery, smeared out focus or with not in focus? Well, of course, you want a nice in focus picture. We want the same thing with our telescopes. So what we want to do is to try to minimize the distortion that we see in our pictures. And it turns out that one of the main sources of distortion in pictures of the sky is the Earth's atmosphere. You can think, well, this telescope, we're at the bottom of the atmosphere, and we have to look through the Earth's atmosphere to detect all of the sources up in the sky. So if we can minimize the distortion that's produced by the Earth's atmosphere, that gives us better data, better quality data with the telescope. Long story to explain why we have these big vent gates on the side of the dome. We open them up at the beginning of the night and we let the air flow through the dome. And what that does is that has a big word called equilibration. What that does is it makes the temperature of the air inside the dome the same temperature as the air outside the dome. And that minimizes the distortion that we see because of that. So it's a bit of a quirky looking telescope, but it has a real purpose. And the second purpose of this image is to show you all how big this telescope is. One of my colleagues is hiding in that picture. Can you see her? Can you see her? Can you see her? Her name's Naibi. She's got her PhD at the University of Florida, where I did a few years ago, and she's a full-size human. Promise, not and the whole nine yards. Let me go to the next slide and show you. There she is. Oh, hi, Naibi. Hi. And that's after we had to wave and say, Naibi, please wave or something. We can't see you very well. And you can see there she is right in the center of the frame standing there. So there's a person. Let me go back real quick. See, boom, she was hiding right here. You can just see her head and shoulders in the picture right there. But again, just to give you an idea how big the dome is and how big the telescope is inside the dome. Let's show you a picture of the telescope itself. There's a computer drawing of the telescope, not a real photograph. And look, I just wanted to tell you a couple fun facts about the telescope, including the way that astronomers, the way that we measure how big a telescope is how big is the mirror inside the telescope. And in this picture, this computer picture, the telescope mirror is painted this kind of yellow and orange color. I don't know why they did it, just so it would stand out so we could see it. And in the real telescope, that mirror is 27 feet across. 27 feet. People, I will bet you that mirror is bigger than the room that you're sitting in. Well, maybe if you're sitting in a big classroom or an atrium somewhere, not so much. But a normal size room, that telescope mirror wouldn't even fit inside there. The whole telescope, from the ground up to the tippy top, is about 72 feet tall. That's huge. That's as tall as a 5-story building. 5 stories, this telescope. When you go in and stand next to it, you look this big. You look really tiny standing next to it. And I want you all to come and visit Willamette Hall on the University of Oregon campus once it's opened back up, and we'll show you exactly how big the telescope is. I'm sitting in my office and I'm looking into this massive atrium, which is inside this building, and this telescope will barely fit inside the atrium in Willamette Hall. And I saw my colleagues, Laura, shaking her head going, what? Right now, because she knows that is a massive atrium. By the way, it's about, again, 5 stories tall, that atrium. So just to give you a hint about how big the telescope is, but what if I showed you the telescope instead? Bam! There you go. There's the telescope. Everything that's blue in that picture is the telescope. And by the way, you can see a fine young astronomer standing there in front of the telescope. You look at the forehead. See, you're going to recognize if you check out the forehead. There you go. That's me. There's a picture of younger me. This is oh my gosh, this is probably 15 years ago that we took this picture. In this photograph, the telescope is tipped over. It's actually tipped over like this, and it's coming out of the picture. So if this was 3D, you'd see that telescope kind of sticking out. And let me show you the mirror. You can see my mouse again moving. That I'm tracing out the mirror. And again, I'm not the shortest dude in the world. I'm about 6'4". And if you look me, they're 6'4", and a little more than 3.5 of me. Well, actually more like 4.5 of me would take 4.5 me's to go across the mirror. And so again, that's a pretty big thing. And the whole telescope moves. Everything that's blue, you see, can move like this, and then the whole thing can rotate. And that gives us the ability to point the telescope in the sky wherever we want. And by the way, if we have a minute at the end, I'll show you a movie of the telescope moving. So look, let's show you what I can't resist. I got to show you one more picture of me. Oh my gosh, there he is again, that guy. And again, that's before I had this lovely facial hair, but back in the day. And that's me using the telescope. It's like you don't even go up and look through your eyeball anymore. What you get to do is sit down in this nice warm control room that's about 3 stories underneath the telescope and look to run a bit. By the way, this was the 4th largest telescope in the world. So this is a pretty monster machine that I got to use. And what does it take? Let's see, 1, 2, 3, 4, 5, 6, 7 monitors, a laptop, 2 keyboards, 2 mice, 2 ink pens, and your trusty calculator, because you know you're going to get some calculating on when you're sitting there working on the telescope. But the telescope has a digital camera. By the way, it has a camera that's very similar to the camera that is in our cell phones. You know, by the way, if I look right here, you can see the little camera lens on my cell phone. But the difference is that, like, maybe my camera, I got kind of a junky old camera. I think at 6 megapixels or something in my camera. The camera at Gemini's got 120 megapixels. So it's the same technology, but just bigger and kind of science versions of the technology that we use, that we have carry around in our pockets. And I think that's pretty neat. And by the way, if I wanted to take a picture with the telescope, you see the mouse here in my right hand, I could click the button and boom, right here on this screen is where the picture that the telescope, whatever the telescope's looking at, appears right there on the screen. So not a lot different of using your cell phone. You know, boom, you hit the button and you can see the picture immediately on your screen. Same sort of thing when you're using the big telescopes in the world. You get to sit there. So the point being is that if you're comfortable using your cell phone and the technology in your cell phone, it ain't much different using at these big science facilities like this. Don't be so scared of this stuff. Don't get nervous when you see 7 monitors and 2 keyboards. You go, dang, that's awesome. I want to sit in front of a computer that's got 7 monitors and 2 mice and 2 keyboards. Don't be nervous about that stuff. It's just a computer. And by the way, the best thing about it is you've got a whole team of people that will fix the computer if you break it. So anyway, don't be nervous about that stuff. Get in there and check it out.
John, I have a question for you.
Yes, ma'am.
Questions. So tell me a little bit more about when you're taking all of these pictures, what are you doing with those pictures? Who gets to see them? And what kind of calculating do you have to do? How does that play into?
No, thanks. So look, that's a good question, Laura. And let me give you the short answer. So any US citizen can apply to use Gemini, even me and you. And now what we would do is we would write a proposal that says, hello, Gemini, we would like to use the telescope to do this project. And that proposal is then ranked by a group of astronomers. And if your proposal gets top ranking, boom, you get the telescope time. Then you at your home at University of Oregon, for example, we here in Eugene, you and I would get together and we would build our observations in a little app. It's actually called the Gemini app, believe it or not. And we would build our observations and then send our observations to Gemini. And a person that works at Gemini, like I used to, would take your data for you. And then maybe a month or 6 weeks later, you get an email that says, hi, your Gemini data is ready. And you download your data and start analyzing it yourself. So there's how it works. Now, what did I do at the telescope? As the person that was taking the data, let me show my mouse again. This little window right here is showing the observations that the scientists built, and then I was running the observations for them. So at the telescope, I was literally taking the pictures that we would send to the scientist. now. So lots of folks get to see that data. And by the way, when you do that, that data becomes, you own that data for 1 year. And then after 1 year, it becomes public. So right now, me and you and any of the students that are watching on this video right now, we could go to the Gemini database and download Gemini data and work on it on our own for free, by the way, and just do it. So the data becomes public. Sorry, it's a long answer. No, you the one part about the calculating. While we're sitting here on the fly, and as I'm taking the data, I get to do a little quick analysis of it right then. So for example, what I might use my calculator for is, let's say we took a picture, but the object that we were trying to detect, it was too faint. So I might do a little calculation to say, hey, we took a picture that was 10 seconds this time and it didn't work. How long do I have to take the picture to get a better result? And so, you know, it's fairly straightforward math. It's just algebra, as a matter of fact. But you learn that stuff before you go to the telescope. Then while you're there, you can do it on the fly pretty quickly. Yeah. Oh, hold on. I think we got something in the chat. Oh, okay. Josie just asked, we got lots of questions that we're going to save for the end because they're kind of general. But that's excellent. Thank you, Josie. Yeah. So look, let me show you something else about this thing. So again, there was that. So there's that guy. I think this is the last picture of me. I promise nothing, but I'm pretty sure it is. But let's switch gears real quick. And I can't resist. I want to show you a scaled solar system. Oh, hold on. Oh, we got a good one. What would a good proposal for Gemini look like? Excellent question, by the way. You know what? It looks an awful lot like a book report. As a matter of fact, there's 3 parts of a proposal. One of them is about a 2 to 3 page essay where you get to describe the project you want to do. For example, one thing that I love is I love Saturn. And I love the moons of Saturn. The moons of Saturn are some of my favorite things. And I even have a favorite moon of Saturn called Enceladus. Enceladus. I double duck dare you to go to Google and type in Enceladus and see what cool stuff comes up. So anyways, the point is you write a couple page a proposal about the project you want to do. Then you build your observations in this little app. And then you have references and citations that show where did you get the information to build your proposal. And that's very important because your proposal then goes and is ranked by the astronomers, and you want to put in a good one so you have a chance at the telescope time. Let's see. Oh, I got another good one, a question I've answered in the past. Do you have to be good at math to be an astronomer? And that's actually, I'm going to be cagey, and I'm going to say yes and no. If you want to be a PhD astronomer and do what I did, excuse me, which was, you know, be a researcher and develop these programs and use the telescope, you got to be pretty mathy. You know, you got to don't get so nervous right now. Y'all are pretty early in your education here, but I liked math. So when I was in high school, I went through algebra and went to pre-calc in high school. And then when I got to college, by the way, I went to a community college in Florida where I got a 2-year degree. And while I was there, that's when I first started studying a little bit of calculus. And then when I went all the way and got my PhD. So look, yes, some ways, but there are other jobs at telescopes where you don't need to be quite so mathy. I think that if you want to work at a big place like Gemini, you probably at least have to know a little algebra. So you better go through at least Algebra 1 and Algebra 2 if you want to. Oh my gosh, then we got one more question. I want to answer it real quick. What is the biggest telescope in the world? And where is the best one? The first one is easy to answer, and the second one is, oh, you're painful. So look, the biggest telescope in the world right now, look, there's a couple different kinds of telescopes. The biggest telescope in the world that's like Gemini which is an optical telescope, a telescope that observes the same part of the same light that our eyes can see. The biggest one in the world right now is in Spain. It's actually on an island in the Canary Islands, and just like you, Canari or Canary. Sorry, I was spelling it in Spanish. Islands, and these are a little group of islands that are off the coast of Morocco, as a matter of fact. And there's an island called La Palma, and on top of that island is another cluster of telescopes. And the biggest telescope in the world right now is the Gran Telescopio Canarias. I don't know if that's the right way to say it, but that's the way I say it all the time. And also known as the GTC. And that has a mirror inside it that's about 35 feet across. So even bigger than Gemini. And now you pain me. Where is the best one in the world? All right. First of all, here's my joke answer. The best telescope is at Pine Mountain because it's our telescope and we can do whatever we want with it. But I would tell you what, if to be the answer that an astronomer would give you, Vulcan's honor, would be the Hubble Space Telescope. That one is the best one by far. And by the way, it's tiny compared to Gemini. The mirror in Hubble is, air quotes, only 9 feet across. So it's a lot smaller than Gemini, but it's above the Earth's atmosphere, which means no distortions. And that's why Hubble gets the absolute best data. So anyways, you pain me, students, asking me that. My favorite is Pine Mountain, but the best one is probably Hubble. So look, let's talk about this scaled solar system for a few minutes. And you all come with some more questions. Those were really good. All right. These are only models. They're not the real planets, but they're models that I really like. And one of the reasons that I really like this graph, by the way, these are computer models. These aren't even real. This is all generated in a computer. And the reason I like it is the size of the planets is what we call to scale. So if you took all the planets and you shrunk them down to they were this size, the relative size of the models is correct. And so you see right here, let's count them off. We've got 8 major planets. There's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And here's Earth, and that's the actual size of Earth compared to Jupiter, for example. About 10 Earths will fit side by side across the diameter of Jupiter. And another neat thing I always like to point out is our Earth would fit just nice and snugly inside the Great Red Spot on Jupiter. And so that's a hurricane happening in the atmosphere of Jupiter that's the size of our planet. Yeah, things are a little spooky up there in space a little bit. And by the way, if this doesn't freak you out, hold on to your ducks because this is going to. Here's the same pictures. There's the same exact models with the sun added in. And now look down here in the little lower left corner, there's Earth. That's our entire planet compared to the sun. And here's our first crazy fact that I teach my class, ASTR 122, every year is that 109 Earths will fit across the diameter of the sun. 109 Earths! Who the heck has ever thought of 109 Earths before? It's a crazy idea, 109 Earths. There's only one Earth. But if you think about a little necklace of beautiful little blue beads of little Earths side by side, 109 Earths will fit across the diameter of the sun. That makes me feel a little bit small, to be honest. So look, don't look at the sun. Oh my gosh, students, don't look at the sun. The worst headline I could possibly see in the newspaper would be, 2 students blinded, Dr. Fisher told us. No, don't look at the sun. But the next time it's at sunset, you see that beautiful sun setting down behind the mountains or you're on the coast or something, take a quick peek and look at it. And I want you to remember this the next time you see that. Imagine that little sun up in the sky. 109 of our planets will go across the diameter of the sun. And that takes a little while to sink in, to be honest. But if you think about this a few times, when you don't look at the sun, but anytime you get to glance at the sun and take a peek at it, think about Dr. Fisher telling you about 109 Earths going across. And you know what? There's another thing to think about. Our sun is special because it's ours, but the sun is a star. And the sun is a star just like every other star that you see in this picture right here. And I like to think right now that on some other planet, around some other star, there is the Bizarro sail program. And right now, Bizarro Dr. Fisher is giving a talk to all the Bizarro sail students, and that Dr. Fisher is saying, "Look up in the sky, and our star is just like every other one up in the sky." And I can just think of, oh, maybe they're around that star right there, or that one, or this one right here, or that one over there. And in their sky, our sun would look just like one of those stars that we see on that picture right there. And I think that's kind of a neat thing and to share. Let me see. We got a question. Oh, great question. So when you think about how small you are, does it make you feel tiny or unique? And does it make you feel bad or amazed? And that, by the way, golf clap for whoever asked that question. That's a great question. And I'll tell you, the honest answer is both. I can't answer in any other way. I feel teeny tiny because of this crazy scale that we're talking about. But you know what? I feel unique too. And the reason is now look, I'm gonna get philosophical on you for a second. So, all right, let's have a moment of Zen here. As far as we know, humans, we are the only species in the entire universe that understands that we live inside the universe. That's a little heady, okay? And I like to think that we are the universe contemplating itself, because we are. Where you poke here, look, poke yourself, poke, 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 poke. You're made of stuff. Do you know where your stuff came from? The inside of stars. The stuff that you're made of was cooked up in the interior. You are literally star stuff. You are made of the same stuff that the stars are made of. And because of that, we are the universe. We are the universe. We are made of the stuff that the universe is made of. And here we are sitting here thinking about the universe and how big it is and what it's made of and how old it is. And that makes me feel big. That makes me feel unique. That we have enough up here that we can sit back and think about the universe itself. And I hope that helps. I like to scare you all a little bit about feeling small and tiny, but in the end and in my heart, I feel big because of that. I feel connected to the universe in a real way. And somebody made a comment. It is a little spooky to feel how small we are, but I hope that helped a little bit with you too. Let me show you a couple more slides and we'll do Q&A. Look, this is a picture of what's called a nebula. And you've all seen beautiful pictures of stuff like this up in the sky. And our buddy, look down there in the corner, JP Metsavanillo. I looked him up online, it's a he. And JP is triply cool because he's an amateur astronomer, a photographer, and a computer scientist. And what JP realized, and we know this, we live in a three-dimensional universe. But when you look up in the sky, it's difficult for our brain to understand, to kind of come to grips with how the sky looks. And it makes everything look a little bit like a painting or a picture like this. But what JP figured out is how to take a picture like this and make it do this. Ooh. Well done, JP. He figured out that by making these images into a GIF and by rocking them back and forth, we can trick our brains into seeing the picture in 3D. This is the picture that he took. Then he did some computer magic on it and turned it into that. And I just love this idea of being able to show you, look, when you go look in the sky, those stars, they're not painted on the inside of a dome. We don't live under a dome. That's 3D, that sky up there. And you might have two stars that look like they're right next to each other, but in reality, one of them is much, much farther away than the other one. I just think this is a neat way that JP could sort of trick our brains into seeing 3D. So what do you think? How long have I been talking? Oh my gosh! Okay, hold on. I'm going to talk for 5 more minutes or 10 more minutes and shit. Is that okay?
Yeah, but I have a question.
Go for it.
Well, can I interrupt now?
No, no, we're in a good
Wait.
spot for sure.
All this stuff that you're talking about, I'm so curious right now. What are the really hot research topics that astronomers are really, I mean, like you talked about loving Saturn and studying Saturn, but
Yes, ma'am,
what's really being heavily funded right now?
for
Because
sure.
researchers want to know.
Yep, two topics jump right into my mind. The first one, which is a real exotic topic, is something that we here at UO, a lot of the faculty here in UO physics, do this research, and that's about black holes, and not just black holes, but black holes that merge together, two small black holes that merge together to make a big monster black hole, and that type of study is very active right now because just a couple years ago, a very special telescope came online and started getting data. And here's another thing for everybody to kind of check out online is a telescope called LIGO, LIGO. And if you go to Google or your favorite search engine and type in LIGO astronomy, boom, the very first hit is the homepage for this telescope. And so this is a huge new topic for us because we just developed the technology to be able to make these observations. So there's one, and then another one is a massive topic that's a huge deal in astronomy right now, and that is called exoplanets. And these are planets that are around other stars. And again, I'm absolutely fascinated. This is one of my favorite topics. And let me tell you how big of a deal this is. In maybe not in the lives of the folks that are listening to us today, because y'all a teeny bit younger, kind of maybe high school, middle school folks, but for the students that are in UO right now, they're call it 20 years old. And in the last 20 years, we've discovered 4,500 planets around other stars. What? That's in the That is a crazy, insane thing to think about. Look, when I was a kid, we had 9 planets. Now we have 8. There's a good reason for that. Don't worry. We actually have 14 planets in our solar system right now. But we have discovered 4,500 planets around other stars. It's crazy. And let me say something that I tell in my class. This is such a big deal. This discovery is so big. I truly believe that we, right now, humans, and by the way, students, you all can be part of this. You can be part of this. We are making the map that humans 1,000 years from now will use the map we are making to go to these planets. That's how big this is. This is a discovery that is going to be, I think this is the biggest discovery that we've made in our generation. The fact that we now know that there are planets around many stars, and so many that we actually think that on average there is one planet around every star in the sky. And that is a crazy thing. Now look, some stars have 0 planets and some stars like us have 14. But on average, every star in the sky has one planet around it. And I urge all of us that are listening, not tonight, looks like it might be a little cloudy tonight, but when you get a nice clear night here in the next week or two, go outside and just look up at those stars. And that sky has changed dramatically in the last 20 years. When I was a college student, we didn't know of any planets up there. We were the only ones that we knew of. And now we look up there and there's one planet around every star. That to me is one of the biggest discoveries we've made.
That's amazing. Scott, when you're like, share with me or with all of us viewers what like a day in Dr. Scott Fisher's research life is. Like, how do you do this research? Are you just on your telescope for months at a time, or how? What's that
No,
look like?
no, I like no. Actually, Laura, that's a great question. So it turns out that it might not be what you think. Like you said, what most folks think of an astronomer that I live at night. I'm up at night every day of the month, and we go to the telescope and we look through there and make some notes and yell eureka and all of that. But it turns out that I'm only at the telescope a few times a year, maybe only 10 times in a year do I get to go to the telescope and actually obtain some data. Then most of the time is spent here in my office in front of my computer where I'm analyzing the data. And then once you analyze the data, turns out you have to understand it, and then that means you know working with it, and then writing it up and making posters and publications and things like that. So for an astronomer like me, now look, when I worked at Gemini, I got to be at the telescope all the time because I made observations for everybody else. But as an astronomer, you might only get to observe for 1 or 2 weeks a year, then you spend the rest of the year kind of doing computer work. Don't get me wrong, I love the computer work too. And so really, to be a research astronomer, kind of like me, you could be a little bit mathy, you know a little bit math. But also, I'll tell you what, if you are good with computers, that is a huge benefit in the world of any STEM, physics, chemistry, bio, marine bio, earth science, volcanology, astronomy. If you can combine a little bit of math and a little bit of computer science, do it. That's the way to do it. So I got some questions in the chat. Can I answer them?
Yeah. Would you like me to read them out to you? Would that be easier?
Yeah, sure. Feel free.
I'm really interested in astronomy, but I don't consider myself to be very good at science. Do you have any advice for someone who wants to study something but is scared that they'll do poorly in the
Yeah.
class?
And by the way, first of all, let me say, whoever asked that, you're not alone. Almost everybody who comes into science is like that at first. But this is a little bit above y'all's head, but don't worry about this. There's something called imposter syndrome. And that's really big. And what it just makes you feel like, why am I here? All these other people are so smart, and I'm just like some little guy or some girl. We all go through that. I went through it. I went through it dramatically. And one of the reasons is that I've been very lucky to work with really good people. And what I've learned is you actually want to work with folks who are a little bit smarter than you. And that way they can help raise you up and kind of pull you along with them a little bit. And so I think my advice would be is to two things. One, be bold. Go for it. Go for it. Give it a try. And secondly, start slow. Here's one thing that I noticed that our college students get in a little bit trouble with. We're so excited, we take too big of a bite the first time, and we get overwhelmed and then think we can't do it. Whereas if you started a little slower, maybe you're not ready for Calc 1. No problem. Take pre-calc and get ready. Ramp yourself up, get prepped, and then dive in and go for it. And that's what I would say. Don't. It's a little less nervy than you think. And I'm going to show you something real quick. Won't everybody just hang tight? Oh, don't look at any of this stuff. Don't look. Don't look. Don't look. No. Stop. Here we go. All right, that was quick. But this is relevant to a couple questions that I see right there. Can you all see? What do you see on the slide right now? You see a question? There are.
The staff of research facilities.
There you go. So back at Gemini, there are 110 people that work at 110 people work at Gemini. And by the way, I know this because I called my friend who is the CPA, and they told me there's 110 people that we pay. How many of those people are PhD astronomers like me? I want a couple guesses. Josie, get a couple guesses and type them in the chat for me. So 110 people work at Gemini. How many of them are PhD astronomers like Dr. Fisher?
I'm going to guess 25.
25 is one. Let's see if we get one more in the chat. I'm curious. All of them? Good. 25? Yep. I like it. You guys are doing good. 10. 10. There are 10 astronomers and 100 everybody else that works at Gemini. And by the way, who's everybody else? Mechanical engineers, software people, the receptionist, the person who, by the way, is a science journalist who writes all the press releases for us, the person who does just the computer imaging and sits around and does Photoshop all day, the person who's fluent in English and Spanish and translates all the documents between English and Spanish so we can go between Chile and Hawaii, the CPA, HR, the guy who keeps the fleet of trucks running. Folks, you don't have to be a PhD to get involved in science. You just have to have interest and be a little bold and dive in there and do it. I hope that helps. That's something that's surprising. Folks don't think about that very much.
Yeah. Well, and one of the other questions you're kind of touching on a little bit, but what kind of jobs do astronomers get involved in? And
Sure.
what if you
So
don't have your doctorate?
no, yes, ma'am. So I mean, so the way typically, if you're going to, go and get a PhD like me, then you get a bachelor's degree first, and then mine was in physics, and then a master's degree, and then a PhD. And what many folks will come and get a STEM degree like physics or chemistry or computer science, and then go and work at a big facility like Gemini or LIGO, or you may have heard like, the LHC, CERN over in Europe. But a lot of folks who have science degrees also go in and do things like banking, um, again, computer programming. We have a recent person who graduated from UO who now works at a hospital where they are the technical person that takes care of the MRI machines and things like that. So there actually is quite a wide spectrum of jobs that you can get if you have a science degree. Like, of course, I know the most about physics because that's where I work, but biochem, marine bio, any of those things, you can get involved with a wide variety of topics.
So, how did you get inspired and involved in astronomy yourself? Where did this happen in your career and your life?
Yeah, I'll tell you later than you might think. That's a good question. Look, I've thought about this quite a bit because folks have asked me this question a bunch, and I think that if you ask me how did I become a scientist, I think it was one thing. I, I was a curious kid. I was just really curious. I loved building stuff. I loved taking stuff apart. I built a dam and dammed up the creek and flooded the backyard one time, and built birdhouses and all this crazy stuff and dug trenches, and I don't know. I didn't even know why. I just wanted to, I just love this idea of finding out how stuff works. And the one thing that happened to me where I feel I got real lucky is that never got squashed. Don't let your curiosity get squashed. Students, listen to me. Don't listen to some fool who's telling you not to be curious. By the way, I'm not trying to be mean. I'm just trying to be excited. It was my curiosity that drove me, and then I figured, well, what can I study that lets me be curious? And it was like, well, engineering. I was going to be an engineer first. I wanted to build bridges and skyscrapers and stuff like that, and started taking engineering classes. And by the way, in college, in a 2-year college, just like Lane, for example. And when I got there, I took a physics class, and I was like, now, wait a second. That is really interesting because it's physics that's kind of underneath engineering, that's the basis of all of that other stuff. And boom, that lit my brain on fire. I was like, I got to learn how this stuff works. And so I was a senior in college when I took my first astronomy class. I was going to be a physicist. And when I took that astronomy class, it was like a supernova went off inside my brain because it was like, what? I can study physics and learn about all this cool stuff and build big telescopes and work on machines like that. That was it. Hook, line, and sinker. It was over. And I've never looked back since then. And so let me say something to the students. Don't be worried if you don't have some massive passion right now. But if you have, like a curiosity or something that you like to develop, that's what you need to latch on to. Develop that, and later on in your schooling, the topic is going to come to you. You'll find what to study, and something's going to light a fire under your butt. But you got to have that passion and that drive to get to the point where you can discover the topic.
Oh my gosh.
That's a long answer. Sorry, but
I love it.
yeah,
Curiosity. I always talk about how that is the magic. You're so
it
right. Listen to it.
it,
Yeah.
it truly is. It was what drove me it nudged me into the science world. And then once I got in there, hey, look, look, I ain't gonna lie to you. It's not easy, but it's not hard either, because you're so interested in it. It's just like, I want to do this stuff to learn it, and if you can find a way to cultivate your curiosity or your motivation, that's all you got to do right now. Don't worry about the topic. That comes to you later. Promise it does.
That's awesome. Well, that is segue into another question
Mm-hmm.
that somebody was curious. Do you think we'll ever really know everything about space?
I don't. I don't. And that's actually a hard thing to say. And because let me say something. If you end up kind of working in this science world, there's one thing that's a little bit tough to deal with, and that is uncertainty. There's a lot of uncertainty involved when you're working in the world of research, because you're doing stuff that nobody knows, that nobody has ever done before. And you have got to be okay with saying, I don't know how to answer that. I do not know that answer. I'll work on it and I'll try to figure it out. But being okay with uncertainty is something that I would like to make sure that y'all are that is something I didn't expect as I became a scientist.
That's awesome answer. Well, we're certainly in a week of uncertainty, so I
Yes,
think
indeed. So dealing with uncertainty, yes, ma'am. Yeah.
people are getting used to. So there's a question that somebody says I have to ask, do you think aliens exist or
Yeah, I love it. Yeah, that's a
other
that's a
living organisms?
that's a great question. And by the way, I'm gonna give you the short answer, then the more nuanced answer, which is a little more detail. The short answer is, yep, I do.
Wow.
The slightly more detailed answer is, but I don't think we've ever been visited. Sorry. And nobody wants that more than me. I'm a huge Star Wars fan. I'm a huge Star Trek fan. I love Doctor Who. I love everything that has to do with space. And if some alien landed in front of me at Pine Mountain and said, get on and we're taking a ride, the only thing I'd say is, can I call my mom first to say goodbye? I'm on that ship. I'm going. So nobody wants it more than me. But I just do not accept I do not believe that we've been visited. I don't believe in Roswell. I don't believe in the lizard people running the world. I don't believe in any of that stuff. But let me tell you what I do very strongly believe in. I think that simple life is everywhere in the universe. And I'll tell you what changed my mind about that. The simple fact that we now know that there are 4,500 planets out there, and that there is probably one planet around every star in the sky. That means that there are now billions and billions of places where life could develop. And I'm not sure that it has, but there are these places there. And I think what we're going to find is very simple life, like a little single-celled amoeba, or a little tiny little plankton, or grass, or seaweed, or lichen, or moss, or something like that. I'm now, it is my belief that simple life is probably developed all over the universe, including on Enceladus, the moon of Saturn, which I mentioned earlier. And that's why that's my favorite moon. There is very strong evidence. As a matter of fact, we know for sure that underneath the glaciers that cover Enceladus is an ocean, and there's liquid water there. And at the bottom of that ocean, there is really strong evidence that there might be these things called hydrothermal vents. And if you look just 30 miles off the coast of Oregon, don't go swimming out in the ocean. 30 miles out and about 10,000 feet down, at the bottom of the ocean, there are what are called hydrothermal vents. These are geysers of hot water that shoot up out of the bottom of the ocean into the ocean. And all around those hydrothermal vents, what do you find? Ecosystems,
Right.
complete ecosystems. And I'm now, I don't know, but if you ask my opinion, I think that there are hydrothermal vents under the ice and Enceladus. I think we're going to find simple life there. I don't think it's going to be sharks with lasers on their head. I don't think it's going to be the Borg. I don't think it's going to be the Vulcans. I don't think it's going to be the Mandalorian. It's not. I know that baby Yoda's cute. Don't get me wrong. You know, but I can't accept that. But I think there's simple life everywhere. Again, a long answer, but I hope a good one.
Wow. I hope you're right. That'd be amazing.
No, me too. And let me tell you one last pitch. Right now, there's a spacecraft that's being planned called ELF, ELF, the Enceladus Life Finder. And I want you all to grow up and work on that thing so we can get it launched and sent to Saturn so we can find this out in the next 20 years while I'm still around. Thank you very much.
Yes. Well, a couple more questions.
Sure.
Does light pollution affect your work?
Yes, it does. Frowny face on light pollution. If y'all don't know what light pollution is, it's just excess light that lights up the sky. Look, these folks who have the spotlight in their backyard, and instead of pointing down and lighting up the porch, it's pointing up in the sky. Street lights that aren't lit up in the wrong way and things like that. So it turns out that light pollution is a real big problem. It sure is. But I am happy to say that where Pine Mountain is, out in Central Oregon, it is still very, very dark out there. And we have a little bit of light pollution from Bend and from Prineville and a couple of the little towns around there. But the sky at Pine Mountain is still very, very dark. And we're working on preserving it, as a matter of fact. We're going to see if we can get Pine Mountain designated as a dark sky sanctuary. And if we can, that'll help us keep the skies dark out there. But light pollution is a real thing. Yeah, unfortunate.
Good question.
Absolutely.
Another question is, how does time change in a black hole, and how do black holes form?
Yeah. So of course, you can come and take a whole course on that, but let me give you the short answer. And I saw somebody ask a little bit about movies too, but I love space movies. Oh, I'm a huge sci-fi. And I'll tell you what, I loved Interstellar. Interstellar was one of my favorite movies recently. Look, they did some things real good and actually related to the time question. That's legit. When Matthew McConaughey went away and came back and his daughter was older than him, that's kind of how that works. There's some very weird effects that happen if you get close to a black hole. Now, in reality, we don't have any technology that would allow us to get close enough to the black hole that we would see these effects. But on paper, the mathematics, they say this would happen. So time does get messed up when you get close to a black hole. How do black holes form? That's an open question. We know how some of them form, but we don't know how the big monsters form. There are black holes that are called stellar size, star size black holes. And these are formed when a star that's about 10 times bigger than the sun at the end of its life, they blow up and they are what they call supernovas. And the stars literally blow themselves to bits. And the only thing that's left is the center core of the star. And that can collapse down into a black hole. And so those can form, and then those can merge together into bigger black holes. But that's the only type I know about. I don't know about the ones at the center of the galaxies.
Well, that's pretty. How many faculty members are teaching about black holes on campus?
So, actually here at UO, we're really a big physics school. There's 40 faculty in the physics department, and there's two or three of us that do sort of traditional astronomy with telescopes and stuff. But then there's 5 of our faculty work at LIGO and do this merging black hole stuff. So there's maybe about 10% of the department are really actively involved in astrophysics here.
Wow, that's really impressive. So,
Mhm.
Yeah, back to that movie question. It sounds like you kind of answered that a lot of those really do portray.
Look, in general, look, let me tell you the two best. Let me tell you my top three movies that kind of did it right. And I think Interstellar was one of them. Again, now look, Matthew McConaughey cannot go through the black hole and stuff like that. Okay, that's all sci-fi. The Martian was real good. That was great. The Martian, again, you're not launching off of Mars without a windshield on your spaceship, but still, most of that was real good. And then I loved an old movie named Contact, which was written by Carl Sagan. And that's a great movie because again, he was a scientist that helped direct the movie. And again, so those would be kind of my top three kind of scientifically accurate movies, maybe.
That's awesome. Well, Scott, this has been amazing having your time and
Yay! I'm glad to come and talk to y'all. I hope it was okay.
oh, fantastic. And if anybody has any additional questions, certainly email salesstaff@uoregon.edu and we can
Yeah, forward them to me and I'll answer them up for you.
yes.
Happy to do so.
Is there any last little tidbits you're going to leave us with, or just be curious?
Um, that was what I was going to say. No, no, I'm just kidding. Look, students, I really appreciated the questions you asked about a little bit about being nervous and how do I get involved. I know I'm just another old, like bald white dude that's talking to you, but I've been through this. And look, and I was you. I would look, I was a fairly poor dude. I went to community college because I couldn't afford college. I stayed at home, you can do it. You can do it. I'm not much smarter. I might be a little. I got a big head, but other than that, I'm not much smarter than anybody else. It was the curiosity. Don't let anybody squash your curiosity, and just go for it. Let me look up this word for me. Proactive. If I want you all to be proactive, you go reach out and grab that pre-calc class and shake everything you can get out of it, and don't you let anybody squash your curiosity. And you keep in touch at Pine Mountain, and next summer you come up there and you visit Pine Mountain with us live, so me and my students can show you around and give you an elbow bump. How's that sound?
Sounds awesome. We so appreciate you.
Thank you all. You invite me back again. I love doing this and talking with y'all.
Awesome. Have a wonderful rest of
You
the
too.
day.
Thank you all. Let's go Ducks.
Go Ducks!
Bye, everybody.
Oh my gosh, that was so great.
That was great. That's a fun Doug. You got to keep me on the list.
I will absolutely, and we're gonna have to figure out how we get to bring people to Pine Mountain with you. That would
Yes,
really
ma'am. Look,
oh,
even if things are slower than we want, we'll do remote observing in the spring.
okay.
Yeah.
Well, that sounds great. Well, I'll let